Hello, analysis students. So there was demand that I go through the proof of one last theorem that we didn't make it to in the notes. Namely, I believe it was called Theorem 3 in the notes, which says, for any function f from u to r, and any limit point p of that domain u, the limit as x approaches p of f of x is equal to L if and only if for every sequence x sub n of elements of u different from p, with the limit of f x sub n equal to p, it follows that the limit of f of x sub n is equal to L. And let's go ahead and do that. So there are going to be two different directions to prove. So let's start by, well, I guess we better let u be a subset of our f from u to r be a function. And p be a limit point of u. In the forward direction, we also get to assume that the limit as x approaches p of f of x is equal to L. And we want to prove something about every sequence of elements of u different from p with limit of x sub n equal to p. We want to prove something about those, so let's consider any one of those. Let's let x sub n be a sequence of elements of u different from p. And let's further assume x sub n converges to p. And what do we want to show? We want to show that the limit of f of x sub n is equal to L. Well, how do you prove a limit statement? Well, let's consider any epsilon bigger than 0. I need to come up with a choice of big N. And how will I do it? I will use this assumption and that assumption. So let's see, since limit as x approaches p of f of x is equal to L, there exists some delta bigger than 0, such that for all x in u, if the absolute value of x minus p is less than delta, but bigger than 0. Remember, the limit doesn't care about what happens when x is literally equal to p. Then, absolute value of f of x minus L is less than epsilon. So let's go ahead and number that implication. Secondly, well, this delta is bigger than 0, and x sub n converges to p. So there exists some big N such that for all little n bigger than big N, absolute value of x sub n minus p is less than delta. Let's call that 2. So now what will we do? Well, we'll consider any little n bigger than big N. So, by 2, absolute value of x sub n minus p is less than delta. Since x sub n is in u but is not equal to p, absolute value of x sub n minus p is bigger than 0. Thus, by 1, since right now we have 0 is less than absolute value of x sub n minus p is less than delta, and x sub n is an element of u, it follows that should be a period. Absolute value of f of x sub n minus L is less than epsilon. So what have we done here? Well, we've shown that for every epsilon bigger than 0, there exists an n, namely that n, such that for all little n bigger than big N, absolute value of f of x sub n minus L is less than epsilon. Hence, f of x sub n converges to L, exactly as we claimed. Nice. Of course, this is only half of the proof. Let's do the other half. And let's see, maybe I'll do that so we can keep this statement up. So this time we want to show that if for every sequence x sub n of elements of u minus p, the limit of f of x sub n is equal to L, then we want to show that the limit of f of x is equal to L. And just like we did in class, instead of proving that statement directly, we'll prove its contraposition. So what will we do? We will suppose not limit as x approaches p of f of x is equal to L, meaning that I'm assuming the limit is different from L or the limit just straight up doesn't exist. And let's take a moment and see what that means. So thus, what do we get? We get not. For every epsilon bigger than 0, there exists a delta bigger than 0, such that for every x in U, if 0 is less than the absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon, and let's negate that. So there exists an epsilon bigger than 0, such that for every delta bigger than 0, there exists an x in U such that, and then we negate the implication, such that the hypothesis of the implication is true, and the conclusion is false. And let's go ahead and number that. I'll call that, nope, one's already in use. This is going to be called equation 3 now. So I'll write a 3 later on, and that'll refer to this line. Now let's write down what we want to show. We must show not for every sequence x sub n of elements of U different from P if limit of x sub n is equal to P, then limit of f of x sub n is equal to L, i.e., in other words, we must show there exists a sequence x sub n of elements of U different from P such that, negate the implication, limit of x sub n is equal to P, and, well, let's see, let's say it this way, f of x sub n does not converge to L. But I don't want to say limit of f of x sub n is not equal to L, because that makes it sound like I want to show that the limit exists, which it may well not. So that's what we need to show. Well, let's do that. So let's, back to black. Let's take the quantity epsilon bigger than 0 from 3, namely this line. And this line tells us something is true for absolutely every trace of delta. So I'll make a particular trace of delta. I'll take delta to in fact be a sequence of positive numbers. Let's take delta n to be 1 over n, where n is a natural number. Then by 3, for each of those natural numbers n, there exists an x sub n. That sub n is encoding that this x depends on that delta depends on n, so that x depends on n, such that 0 is less than the absolute value of x sub n minus p is less than delta n, which is 1 over n, and absolute value of f of x sub n minus L is bigger than or equal to this quantity epsilon. And now let's just unravel this and see how we can get what we want. Oh, and I guess this x sub n is an element of u. That's important. So let's see, we need a sequence. This x sub n is a sequence. It needs to be a sequence of elements of u different from p. So let's see, since x sub n is in u, and 0 is less than the absolute value of x sub n minus p, the sequence for all n x sub n, the sequence, is a sequence of elements of u different from p. Alright, well that's good. We have a sequence of elements of u different from p. We need to know that the limit of x sub n is equal to p. Well, check it out. It looks like absolute value of x sub n minus p is less than 1 over n, as 1 over n tends to 0. The squeeze theorem implies that absolute value of x sub n minus p must converge to 0, so x sub n converges to p. There's more than one way to write that down, but it's all really the same logic. Next, we need f of x sub n to not converge to L. Let's see, for all n, absolute value of f of x sub n minus L is bigger than or equal to epsilon. But notice, if f of x sub n converged to L, this would get less than epsilon eventually. So that this is true for absolutely every n. That tells us that f of x sub n cannot converge to L. It might converge, but not to L. And that's just closing statements. Yeah, I'll use this paper. So let's summarize what we've done. So what have we shown? We have shown that if f of x does not converge to L as x approaches p, then there exists a sequence x sub n of elements of u different from p such that limit of x sub n is equal to p and limit of f of x sub n does not equal to L or does not exist. Thus, not limit x approaches p f of x equals L implies not for every sequence x sub n of elements of u different from p, if xn converges to p, then f of xn converges to L, and by contraposition, this means that the limit of x sub limit as x approaches p of f of x is equal to L if for every sequence x sub n of elements of u different from p, if x sub n converges to p, then f of x sub n converges to L, completing the proof of the theorem. Nice. Well, hopefully this is useful. Enjoy your day off. I will see you again on Monday.